Okay, all right, just to remind you, you have to be a little careful about kind of untangling all the various things you've seen, because there's often multiple ways to represent all of this stuff that sometimes they're really the same thing and sometimes they're not. So, so we started talking about operators, and an operator is, one way to do that is in its basis. This only works in its basis, is to do this. Okay, so, oh, sorry, that has to be on the inside. So eigenvalue times Keprov. Okay, again, the only reason, now A has to be an eigenvalue of the operator, or this doesn't work. So just heads up on that. Okay. And then we started doing things like saying, oh, that's SZ plus, SZ minus. Anyway, so you can use this to build up operators. Okay, now SX, we went through SX last time. Relatively simple. You saw it get a little bit more complicated, and where it's going to get a lot more complicated is now, since we live in 3 dimensions, I have to do this with X and Y. So we've done Z, now we're doing X and Y. Now the problem with X and Y is that we're going to still work at the SZ basis. I have to pick a basis, right? You have to. So I just picked Z. And you can't cheat by working with SX and the SX basis. That's just working in circles. It doesn't really solve anything. So I talked a little bit about some of the issues with that, mostly being that what was kind of interesting is my Hilbert space is up and down. It's SZ plus SZ minus. That's why that's my basis. Now that works relatively easy with Z. But now, what do I do when I've got 2 more vectors? When I've got X, Y, and Z in a basis of up and down. It would make a lot more sense if I had up, down, and some other direction, 3 directions to describe X, Y, Z. Right? You see what I mean? I've got a problem where I've got I live in 3 dimensions, but I've got a basis set that's only 2-dimensional. So this is ultimately why this is turning out to be a little difficult. How do I describe 3 orthogonal vectors using only 2 vectors? The answer is you kind of can't, right? That literally is impossible. And I'm saying that because we're going to start building towards the uncertainty principle. And hopefully you know the uncertainty principle. Hopefully you had it in your undergrad. If not, it's in my little silly textbook. And if not, if you haven't actually looked at it, you can't know where something is and how fast it's going. Right? So you've heard this stuff. There's also one for time and energy, by the way. We're going to get there. Okay, so again, the difficulties we have, the reason I'm doing these phase factor things, is that I'm struggling to figure out how to make all this work together, how to make X, Y, and Z work in a basis set that's only 2-dimensional up and down. Okay, last bit I want to say one more thing about phase factors, because in any PChem seminar, you're going to hear phase this, phase that. And it unfortunately, that can mean, I can't define it because it can mean multiple things. So there's that, sorry. When it came to these, hopefully I gave some demos, I moved my arms around like a crazy person, hopefully you remember that. Let me give you one more demonstration of a phase factor. And so don't worry so much about this. I'm going to show you a little bit about NMR, just a minute on NMR. Because NMR, like on a proton has a nucleus that's spin up and spin down. It's identical to an electron, right? Okay, so maybe you don't need to write this down or anything. I just want to show you how it works, right? So a proton has a spin, and in a magnetic field, let's say the line's upward. I guess it would actually, the magnetic field would be downward technically, right? So up, down, right? So I won't draw that anyway. So the proton is in a magnetic field, and some small population of them is slightly polarized among all the protons, all mole number of protons roughly. Slightly more pointed up and down. Okay, whatever. Now, the way a 2D Fourier transform NMR works, and all of your NMRs are Fourier transform NMRs, is that, here I'll call that X and this is Y, or Z is Z. The way it works is, you hear about a pi, I guess that's a pi halves pulse. What happens is that you turn the magnetism with a radio frequency burst. So that big cabinet next to the NMR is the magnet, there's a big cabinet next to it. It's a radio transmitter. That cabinet sends a radio wave burst to cause the magnetism to flip on its side. And then what happens is, because of the uncertainty principle, and we're going to get to that, so it's up, it's now, sorry, let me mimic what I've drawn, it's now this way. Now the uncertainty principle says that I have a little too much knowledge. I know where it's pointed up in Z. It's not. It's in the Z equals 0 plane, so that counts. I know where it is in Z. Z equals 0. I know it looks like the X vector. It's pointed to the X vector. Okay, as we covered the uncertainty principle, that's too much information. You can't know where a spin half system is pointed in X, Y, and Z simultaneously. We're going to cover some of that today. Anyway, so what happens is it starts to turn. That is the trick, right? So it turns out of the way. And you don't really know. So when you see this, you notice I drew it this way and this way. You don't know which way it's turning. Okay. Now as the magnetism starts to spin in this plane, a spinning magnetic field generates an electrical current inside of the coil. Well, guess what? See, there's a copper coil that surrounds it. Right? The NMR tube is in a copper coil. And so that spinning magnetic field is picked up and generates a current in the copper coil. And that's, again, what that giant cabinet does to magnify that current. Okay, so anyway, that's how the Fourier transform NMR works. And the signal, when you're taking NMR, if you haven't done this already, you see something like this. This is the signal, the Fourier transform, that gives you your NMR spectrum, right? Do any of you see where a phase factor appears? So there's actually a phase factor here. In fact, when you are adjusting your NMR spectrum, when you first tell it to transform it, you might see something like this, and then you transform the phase, and then you get your normal looking spectrum. That's a phase transformation. So where does phase? Any of you see where phase appears in my drawing? Any idea? Based on what I drew, are you thinking about last time? As an angle?
Where it's pointing.
Where it's pointing. I said up, okay. But I drew it exactly in the X direction. Who says that's what it does? Right? I mean, okay, if I which way is it going to fall? I don't know. It could fall anywhere, right? So notice that I could have said it was down here, right? So there's a phase relationship. There's an angle there somewhere. Now, what I've drawn here is I decided to put it in the X direction, but it didn't have to be there. Now, let's say it was in this direction. Let's say it happened to turn out in the Y direction. So again, the radio wave pulse knocked it over, and it actually was at a different phase than what I just drew. You know what you get? You get this. You would get a different signal. That's what phase does. And then so that spectrum might have looked like this. You know, it would have come out differently, and you're still going to phase correct it and get it right. But anyway, but it won't be the same. Okay, anyway, I just wanted to go again over a little bit about what phase means in PChem, because it's never, I just never have seen it properly explained. But now, and of course, what you've also seen, this is decently applicable to what we're talking about, because NMR and NMR spin of protons and electrons, they have the same spin. They're identical. So that was very applicable, but other things are different. Okay. Now recall that what I've done here is so Sx in the SC basis, there's a phase relationship in plus and a phase relationship in minus, but it's relative. So e to the I something, what could that something be to equal 1? E to the I 0, right? E to the I 0 is 1. Okay, so the phase relationship is e to the I 0, and this is, as you'll see, just some angle off from that. And I did the same thing here, but notice these are not the same phase angle, because that doesn't make sense. They're definitely not going to be the same phase angle, because then they're both Sx. Right? Sx is x, Sy is y, so that's why the phase angle won't be the same. Okay, now the next thing to do is notice that we are going to get the proper. This will be true. This will be true for y. Let me just write. This for Sx. Okay, so this relationship means that you still have plus minus are orthogonal. X, y. The same is true for y. I'm not going to write that down. Notice that with this relationship with these kets, we're also able to define the Sx operator. And here it is. And on your homework, I had you doing stuff like this. Not exactly this. Of course, you're hopefully okay with the fact that I'm going to be just using minus and plus because it's painful to keep writing Z tab all the time. Okay, so that's the Sx operator, Sy, the Sy operator is the same thing. Let me double check. With the different angle. And again, crafty veteran that I am, I already see, one thing is already very telling to me, which is that these operators have matrices that are not diagonal. Sx is plus plus minus minus, plus minus minus plus, so that means that these are off diagonal. And that means that plus minus are not the eigenstates. Sz plus Sc minus are not the eigenstates of neither the Sx or Sy operator. We don't need to worry about that right now, I'm just saying that's what it is. Okay, so now we've got all these relationships, and what we want to do is figure out what the phase factors are. And one reason to do this is mostly because, I mean, it's not like it's not known. So I'm going to do plus, just plus. Okay. So to make this work correctly, we're going to go through some Stern-Gerlach devices. We're going to create a polarization, positive in the X, and then we're going to go through a Stern-Gerlach, another Stern-Gerlach in Y, and out comes is polarized in the Y direction, 50-50. We don't need to worry about blocking it. We're just, the measurement is 50-50. Okay, so again, if Sx plus polarized silver atoms go into an Sy apparatus, they're 50-50 split up and down. Now that, I can tell you, is enough to define, it doesn't define these angles, it defines the relationship between the angles. it'll define how one is different than the other, which is good enough. It will just make up a number for one of them. That'll make more sense when I do it. Okay, so again, this is what the experiment does, and now I can get rid of these e to the I, delta 1 and delta 2, because they're 1. Okay, from this, what you see is that the projection of sy plus of an x of x plus has got to be absolute value. It's got to be 1 over the square root of 2. Well, here, let's just do that. Experimental realizations are always absolute values of quantum mechanical measurements. Remember, inner products are what you ultimately are doing with quantum mechanics. These are numbers. So maybe there's an operator in between, whatever. The absolute value of some kind of inner product is ultimately what quantum mechanics is supposed to tell us. You may choose not to, but that's a different issue. That's an uncertainty principle issue anyway. So, if Sx plus goes, remember I have you do this on your homework. You can, equations, things that are real have real meaning. That's one of the, why I'm asking you on that homework. If Sx plus goes into a Stern-Gerlach y, how much comes out up in y? The answer is half. So that's what that means in words. Okay, so I squared the bastard. Okay, you're gonna love this. All right. Okay, plus. I am gonna write the sy, state. Sy plus state. Sy plus state right there. Okay. Lots and lots of brackets. Inner product with Sx. There we go. Now don't make those angles the same. Those are not the same. Okay. A lot of squiggly lines. But ultimately, now again, I really hope, especially on this homework, you're really getting what Dirac notation does. Plus that FOIL. Plus 1. Plus minus 0. Ta-da. Right? I know all these squiggles, all this ink is onerous. But once you start foiling it out, it just really gets simpler and simpler. Okay, 1 over the square root of 2, 1 over the square root of 2 is a half. I can actually bring that out as a thing. Okay, I've got a plus right there. Plus minus plus, those are 0. I'm not even going to worry about them. And now you can see how I was saying how I'm going to define a phase relationship between delta 1 and delta 2. I gotta square it, right? Square root of 2 is 1/2. Square it 1/4. You can see I brought it outside of the square, so it's 1/4. See what I have. There we go. All right, almost there. Take this damn thing, and I won't presume. Tell me if you're having trouble seeing this. Sometimes I see somebody crane your head. You told me before you wouldn't have trouble seeing this. Okay. That's the number 1. I didn't. If I'm going to do this, I gotta go all the way, right? Sorry, I should have had that. Okay. Now we got to FOIL this out, 1 plus that, FOIL it out. Except you also got to remember, actually not really, you can't really FOIL it out. you've got to, I haven't done that yet. The reason is, you've got to make sure that you handle the absolute value correctly. Right? Plus I minus I, right? Now you should be well aware to see absolute value squared, assume everything's complex, and they definitely almost always are. So you're going to have one with the i's as a plus, and another one with the i's as a minus. I'm going to bring over the 1/4 over to the other side by multiplying by 2. Okay. Can I write here? Can you see it? You guys, yeah, okay, so you can see it, so it's your fault. Okay, I'm just going to tell you real quick what this is going to turn into is 2 plus 2 cos delta 1 minus delta 2 equal to 2. Okay, so you're going to have e to the ix plus e to the minus ix. That's 2 cos. So I did some algebra ahead of time. Okay, now therefore, 2 plus 2 cos equals 2. 2 cos, that delta better be 0. That means, and that can only be true is if this is pi halves. Okay, now, because these are somewhat arbitrary, like I talked about a pen falling over, you can say that delta 2 is pi halves minus pi halves. Yeah, minus pi halves. Yeah, that works. Okay. Sorry, yeah, if you don't mind, let me go over here. Yeah, I gotta make some room. Okay. And you've actually seen this before, by the way. Let me sure. Yeah. Go. And Sx is, why did I write that? I don't know why I did that. Okay, now again, I'd actually shown you this before. But I want you to know where it came from. Also, it's an exercise in how to do this stuff. That's another reason to do it. So one reason I go through all this rigmarole is for you to practice. And also understand a little bit about what phase factors are, because again, every pchem top, you'll hear phase this, phase that. That's what it does. And also, you got to learn, if honors, you can start to see that, there we go. You also got to learn not to make presumptions. When you set up things, you have to be really careful that you don't start making presumptions about how things work, and then go from there. If you make a mistake in the assumptions, then everything else is off. So no matter how good you are at doing this or that, everything's off. Okay. And it's all right? Okay, now let's do all this with matrices, because ultimately I do find matrices easier, but what is unfortunate about matrices is a little bit harder to imagine the Stern-Gerlach device. What I lose personally is the ability to imagine atoms running through a magnetic field and stuff happens. So it disconnects myself from the physical reality, which is a little bad, but what are you gonna do? Okay, now, with this stuff in hand, let's take a look at, here. So we're going to define gamma delta 1. Delta 1 was 0, delta 1 was 0, so e to the 0 is 1. And e to the minus I pi halves apparently is I. sure I can Google that. Okay, now I can just look at this and generate the XX operator. Note that this is not the same as what you're doing on your homework. This is just, this operator's job is to take a state and spit out what the SX polarization is, and it better return the same state. If not, then the eigenvalue equation is wrong and you're not learning anything. Now that's a separate issue though. All I can do is generate the SX operators. We're not going to worry about whether it does or does not work in the eigenvalue equation. That has to do with the uncertainty principle, which is what we're about to get into. Okay, anyway, now I can look at this, okay, very quickly I can see that there's an h bar over 2, and again, I'm kind of bad about forgetting to put that in, but I do not see a plus plus or a minus minus, so I automatically know the diagonals are 0. I do see plus minus minus plus. I'm not quite sure which one's which. I think this would be lower left and that's upper right, I think. Although I have to admit I'm a little blanked out. One, because I put the h bar over 2 up front. There we go. That's y. And let's see here. Oh, yeah, so that's 1. But that's the number 1, and that. Wait a minute. Hold on, I think I messed up. This has to be, that was plus, this has to be minus. Sorry about that. I forgot these things were here. Is that right? Let me check on those. I feel like I'm cheating. Yeah, sorry. You see, if this was e to the angle, e to the I angle 2, this was minus e to the I angle 2. So there's no way they could be, they both can't be I. Again, you can just put this in Google. In Google, if you seriously type E parenthesis I times pi parenthesis, Google will tell you what the result is. Okay. All right, now I got to look at this thing. And if I recall, actually, I think what I said before was wrong. Based on my notes, this is upper right. So that means, all right, so again, the diagonals are 0. So that is the SY operator. There we go. 1, yeah. Okay. Just remind myself, because I'm kind of going nuts here now. This is plus, minus, pretty sure I got that right. No, I'm certain I got that right. Plus, that minus. Okay.
Should the top right be plus minus?
Huh?
Should the top right be plus minus?
No, sorry. Yes, this one, sorry. Yeah. Ah, sorry. Okay, what I do makes sense. So that bottom left is clearly only okay with this one. Yeah, all right, it worked, right? I just got worried. I really felt like this was the bottom. I think I even said that this one is the bottom. I thought this was the bottom left. I said that earlier. It's not. That's the bottom left. And I know that once I take my time. The only thing I do really remember is that it's the bra that changes in the matrix. If this bra changes as you go down, then the ket is got to go the other way. There's no choice. So anyway, so I can remember to change this one this way. Automatically, that means that the ket changes that way. And now I have to find the matrix. And sure enough, when I look at my operator, the i's are in the right spot. See, this one, It doesn't matter, they're both 1. But this one, it matters. One's plus, one's minus, so I have to get it right. Okay, but I did. Okay, so now SZ. Hopefully, you don't really need me to do this. Probably seen it. Is 1. See, diagonal. Now, let me remind you again that we've talked a lot about matrices and rules of matrices. I mentioned before, I could automatically see these were not diagonal because they had plus minuses in them. But SZ is diagonal, and it better be because I'm working in the SZ basis. Every operator, when represented in its own basis, better be it better be diagonal. So there you go. Okay, another thing to note is there's these things called Pauli spin matrices. And you will see these quite frequently. As I was blabbering about NMR earlier, between NMR, EPR, and the fact that electrons, no matter what, are spin half, and really is half of your quantum mechanics on molecules and atoms and molecules is overwhelmed by the fact that electrons are spin 1/2. That's why you have to write those anti-symmetric to interchange wave functions. NMR, you just saw me talking about NMR, blah, blah, blah. This spin stuff infects half of what we do. Half of what you do, you have to worry about this spin stuff. Okay, so without the H bar, see, this is a little stupid because when I'm defining this, the Pauli spin matrices, and again, you're going to see them all the time. You're going to see them as Z. You're going to see them defined as sigma 1, sigma 2. The reason it's stupid is that the Pauli spin matrices, they just don't have H bar over 2 in front of them. So this is really kind of dumb. But I have to show you this stuff. It's also part of the homework. Anyway, those are the words for this. Last and also, of course, something I'd already shown you once, but it just bears repeating because you've seen everything at this point. So you're going to have to do a ton of stuff with this, of course, especially on the next, on this homework and the next homework. I'll be a little bit more careful about my constants that I was before. I think I didn't write the constants. 1 plus or minus. There you go. Yeah. Okay, and of course, any arbitrary state is represented this way. And there's a word for this. I won't bore you with it. I'll write it down just in case. I do see this. I do see this written frequently. I do see this a lot. Spinors. Just what they're called. They're just spin wave functions, spinor. I don't know why we got to do it so. Anyway, okay, last bit for your homework. Again, hopefully for those of you who had decent undergrad experiences and you remember it, let me now cover an operation of operators. And those of you who have seen and recall this, you know that we're building up towards the uncertainty principle. And with the uncertainty principle, by the way, one of the things the uncertainty principle tells you, it tells you about these relationships between these matrices, meaning diagonal, non-diagonal. The fact that this is diagonal and these two aren't, that by itself again, I've been doing this for years, no uncertainty principle, uncertainty principles. these guys do not work together. They don't work together. There's an uncertainty principle between Z and the other two. And again, I know that immediately because that was diagonal and that's not. Now you're going to see that, you don't know that yet, I'm telling you. Diagonal, undiagonal, I've got an uncertainty principle. Number two, this one's diagonal, the basis set is the SC basis set. These guys, SC is not their basis set, otherwise it'd be diagonal. We've actually already talked about that, but it's part of the uncertainty principle. Okay, to understand the uncertainty principle, you got to understand commutation, which is when you have two operators. Of course, you're going to be doing, on your homework, you're doing SX and SY and SZ. And we're learning that, of course, with all these foils, plus, minus, minus, plus, blah, 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 you got to get the order right. So this looks kind of stupid. AB minus BA, well, those are the same thing as 0. You've done enough foils of this point with operators that you know that that's actually really unlikely to be the same thing. Right. Plus minus, minus, minus plus, minus blah, 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 right? So I bet you that ain't going to be 0. Now, an anti-commutator, you need this for one of your proofs. You need this for the proof of the uncertainty principle. You're actually going to prove the uncertainty principle. We're going to do it in class, and I'm going to have you do some stuff with it on homework. This one's dumb. No one cares about this. It rarely shows up in quantum mechanics, except in the proof of the uncertainty principle, and you'll never see it again. I've never seen it again. But you need to know it. Okay. Whatever. So, just so you know what that is, I do have to do something with it on your homework. So let's do SX, SY. Here's an example. I may forget that hat. Okay, what's this? All right, you're doing this on your homework. Okay, each one has an h bar over 2, so I'll just go ahead and square it. Factor it out of the rest. Okay, plus, minus, plus, minus, plus. That's a mouthful. Okay. Now I got to be careful with my parentheses. Okay, now y is minus I plus minus, plus I minus, oops. Why did I do it? Now I just forgot here, if you don't mind. If you don't mind, if I just keep going this way. I really hate it on your homework whenever I have to switch to a new line. You might think that that's a different step or something. So I just wrote SY plus. I'm just looking over there. That doesn't look good. That bothers me. Yeah, I mean, it's sucky, but we're actually going to get into something even worse. There's one thing we're going to do that's actually worse than this. Well, look, you're doing this on your homework. Okay, let's see. H bar squared over 4. Okay. All right. Plus, minus, gone. Plus, plus. Okay, that's going to survive. That's going to spit out a minus I. Then I've got a minus, that survives, and a minus plus that doesn't survive. So this isn't actually that bad. So I'm going to go ahead and do this plus. I'm going to start with the plus I because I like that. It's a little bit better. Okay, now let me double check this. Okay, plus I, so it's got to be this one. And I am slamming that into this one. Wait, what? And so, oops. I have minus, that was one. Okay, here, the minus turns to 1, that leaves plus. Here, is that one. And that leaves plus, cancel, that leaves minus. There we go. Minus, now what? Okay. Let's see here. Minus. Plus. Okay, then the only other one that will survive. No. What have I done? Yeah, I think we can. This one, I messed it up. See, I had the same two couplings in the same term, this one, and that's impossible. Sorry about that. That's okay. So plus, where the hell is plus? Okay, I got that right. Then this one couples to that one, so that's plus I minus 1. Okay, I did that right. All right, so this ends up turning to h bar squared over 2 because you're going to end up with two terms that are the same. There's an I in every term now, and you end up with plus, minus, which you should recognize this as SZ. But SZ is h bar over 2 times all that. So this is 2 over h bar. So this is all I times S. No, there's not two terms. What's that? No, there are. Yeah, okay. No, I did that right. Okay, so then this is going to be I. Oh, there's an extra h bar. That's right. H bar squared over h bar is h bar. That's what I got a little confused there. Okay. So you may notice that I had you do this on your homework. I talked about these commutators and anti-commutators. That's how you do them. And I can already tell you, again, this is on your homework. You know, on your homework I had you try to do a little elegant proof. I just wanted to show you a little deeper mathematics, but when it comes to this relationship, what you can do is, and again, you're doing some of that on your homework, for any two operators, any two spin operators that you do commutator, and again, no one cares about anti-commutators. Not that you don't have a relationship. You have this relationship. Okay. This thing, all right, so ijk is x, y, z. You just don't want to spell it out x, y, z. Now the reason is that if this is x, if I is x, y is j, and z and k is z, then this is 1. If it's z, x, y, it's minus 1. Now this would include y, z, x. This includes z, x, y. Get it? And this would be x, z, y, and y, x, z. Right, so you saw the pattern there. Take x, y, z and go forward and backward at an arbitrary stopping point. So this is the forward, x, y, z, x, z, x, y. This is y, y, x, z. There we go. Okay. So anyway, you can just do this a gazillion times. If you have if I is equal to j, then now this is stupid, so don't try to memorize this. That's dumb because what it says is, look at this. Right? If I is equal to j, then you're subtracting the same operator from itself. Okay, so that's the definition of dumb. Okay, now the last bit, let me, now that you've seen this, you can see how to multiply these operators out. I want to point out one thing that's kind of cool, which is that sx squared. If you do all this, I want to point out that what you're going to get, is h bar squared over 4 plus okay, but you know this is the identity operator. So this ends up being h bar squared over 4. Notice that there's actually nothing really to do. You can actually say it's a constant. And again, now that you've been doing a lot of this, right? So I'm hopefully you're not having your mind blown to think about just going through this process as much as it sucks, but it is useful. You show that xx squared would be this. Okay, my point being that if this is true, sx squared plus sy squared plus sz squared. Well, hold on, let's look at this. Okay, why am I writing sx squared plus sy squared plus sz squared? Why am I writing that? Okay, let's go back to middle school. A vector. The length of a vector, the first thing you would do is say x squared plus y squared plus z squared. What's that equal to in terms of the length? Let's call it r, the radius. Okay, so is x squared plus y squared plus z squared, is that the radius? Is it? No, it isn't. It is not. What's the radius of a vector? Huh? Okay, you all just said the radius of a vector is x squared plus y squared plus z squared. That's really quite wrong.
It's the square
root. It's the square root. Right, so this is the vector squared. This is the length squared. Okay. Let's call that the total spin. Okay. Total spin squared. Okay. When you had, and so we can do this. It's actually 3/4 h bar squared. Okay. So there you go. So now you know the total spin of the system. Let me point this out to you. All right. Do you remember doing this? H bar squared L times L plus 1. Do you recognize that? Right, that was the angular energy, or angular momentum. That was the angular momentum of an electron, right? So when we were doing 3D, when we were doing rotational this and that, and we had the angle parts, the eigenvalue for the spherical harmonics was L times L plus 1, and of course multiplied by h bar squared to get the right constant. All right. What if this? And this is angular momentum. Now remember, I said spin is just like angular momentum. We don't think it's actually rotating, but it behaves just like it. So what would this be? What would this be? Now what's S for spin half? path, right? What's this? Did you do addition? Right. So you see it before. All right, let's get out of here. They're waiting. Sorry, I do this every time.